Now what we are gonna study, that will be our ionic equilibrium. Now in ionic equilibrium, we first have to know two things, that is strong electrolytes. So what is strong electrolytes? Strong electrolytes is a substance which completely ionize in aqueous medium are known as strong electrolytes. So what will be? That will be all kinds of strong acid and strong base. Okay. Now second is our weak electrolytes. So what is weak electrolytes? Weak electrolyte is that it doesn't completely get ionized in aqueous medium. So weak bases and acids. Okay. So let's see some acid base theory. That what is acid, what is base, we have to know that. So let's see that. In acid base theory, first comes our Arrhenius theory. Okay. So what does this Arrhenius theory say? That is, those substances which furnishes H plus ion in aqueous medium are known as acid, and those substances which furnishes OH minus ion in aqueous medium are known as base. That means, let us suppose that this HCl, we can just write it like H plus and Cl minus. So here it gives us a H plus ion. So that's why it is a acid. But what happens in case of NaOH? Okay, it gives us this ion Na plus OH minus. See, here it gives us OH minus ion, though that's why it is called base according to Arrhenius theory. Now, Arrhenius theory has some limitations, that Arrhenius theory fails to explain the strength of acid and base. Okay, now most of the theories have failed to uh, explain the strength of acid and base. We're going to discuss this later. Okay, now let's go to the next theory, that is our Bronsted acid base theory. Bronsted acid base theory. Now this theory is very important because they ask you many questions from this, because we're going to see what kind of questions. Let's first see what this theory says, that acids are the substances which donate H plus, and bases are the substances which accepts H plus. Okay, now you can just see it from this theory that it is based on this H plus, this theory. Here nowhere OH minus is seen. So this is the primary difference from the Arrhenius theory and Bronsted acid base theory. Okay. Now we are gonna see what is conjugate base and what is conjugate acid here. Let's see. So here we can see, if this HCl just donate one H plus, it becomes like this. So here this Cl minus is called our conjugate base. That means, what is conjugate base? That is the remaining part of the acid after donating H plus. Okay. So they can give you a question that what is the conjugate base of HCl or H2SO4. So it will be the remaining part after the H plus is removed or donated. Okay, so let's see another example, that is of H2SO4. Now if H2SO4 donates say H plus, what will be it? It will be H plus plus HSO4 minus. Now this HSO4 minus is conjugate base here, right? But this can also donate another H plus and it can become SO4 2 minus. So this is also a conjugate base of this HSO4 minus. So according to SO4 2 minus, it's a acid, but according to H2SO4, it's a base. So it's a very important question for NEET, because they can ask you what is the conjugate acid of SO4 2 minus, so that will be our HSO4 minus. What is the conjugate base of H2SO4? That will also be our HSO4 minus. Okay, so here is our Bronsted acid base theory is also done. Now we are gonna see Lewis acid base theory. It is also an important theory. So what we have to know here, we have to see what is Lewis acid and what is Lewis base. Just like Bronsted acid base theory that was dependent on H plus, this Lewis acid base theory is dependent upon lone pair. Okay, so we all know what is lone pair, that we have studied in chemical bonding. So if some substance accepts this lone pair, it becomes acid, and if it donates lone pair, okay, then it is called base. So let's see which are the substances that can be included in Lewis acid. So first will be the cation of D block element. Okay, so let's write it, cation of D block element. Next is all molecules which have incomplete octet. Incomplete octet molecule. Example given is our BeCl2. Okay, we have all seen it in chemical bonding chapter. Next is our, if the central atom has the vacant d orbital. Central atom has vacant d orbital, just like our SF4, SiCl4. Next is if two atoms of different electronegativity linked by multiple bond can behave as Lewis acid. That will be our CO2, SO2. Now for base, what are the molecules? That is the molecules which have lone pair availability. Okay, lone pair availability. Second is all anions. Okay, because anions also have lone pair availability or electron excess, right? So this is how Lewis acid base theory is done. Now we will come to our last and most important, that is Oswald acid base theory. So what does Oswald's dilution law say? So for that, let's write an equation that is CH3C double OH CH3C double O minus plus H plus. So let's suppose it has initial concentration C, and here it will be 0. So let's suppose it has C minus X, then X, then X. Now this X, let us suppose it will be C alpha. That means degree of dissociation here. We are reading it in ionic equilibrium. So it will be our degree of ionization. Okay. So let's just replace it with X. That means C minus C alpha. Here also C alpha. Here also C alpha. So let's write the equilibrium constant reaction here. That is CH3C double O minus into H plus by CH3C double OH. Right. So what will the reaction will come then? It comes like this. That is C alpha into C alpha by, if we take common of C alpha, it will be 1 minus alpha. So it's come like this if C got cut. So C alpha square by 1 minus alpha. Right. Now if alpha is very very less than 5%, then we can just take 1 minus alpha equal to 1. So then from that it will be like this, k equal to C alpha square, or alpha can be written as root over of k by C. Okay, root over of k by C. Now here is the important thing, that this k can be written as like this. Okay, that is ka by C into the root. So here we are multiplying it with C, and it also gets multiplied with C. So just let's write it again. That is, if alpha is multiplied with C, so root over of k by C into C. But if we take it into the root, then it will be C square, right? So it becomes KC. So you can just see the equation comes like this, or we can, if we just give it a proportionality sign, so it will be like this. So here what do we have? See, that is the degree of ionization is inversely proportional to its concentration, right? So this is our Oswald's law. Now we're gonna study product of ionization of H2. So let's study that. Product of ionization of H2O. Now, since water is very weak electrolyte, so very few molecules are ionized as a particular temperature. This is also called the self ionization. Okay, so if we write it like this, let us suppose this is acid, this is base, because it is self ionization. Self ionization. So H2O, one H2 we are assuming it is acid, and one H2 we are assuming it as base. So it becomes H3O plus plus OH minus. So if we write it like this, the equilibrium constant equation, it becomes like this. Okay, H2 its square. So we all know this H2O has a molar concentration of 55.55. Okay, you can just study it in the first chapter of your chemistry. So it is also a constant, right? Because it's a number. So just we can write it like this, H3O plus, because it's a constant. So if we just, we are taking it as constant. Let's suppose it's K dash. So K into K dash, what will be it? Let's suppose it is called KW. Okay. So we have we have a condition here, that is H3O plus into OH minus equal to KW. Now this value is same at any temperature. Okay, that means the value of H3O plus and OH minus are same at any temperature. So you can just write it like this, H3O plus the whole square. Okay, so from this, what happens if we just take log of it, that becomes the standard state of neutrality for any acid or base. So let's see that. Now at 25 degrees Celsius, yes, what happens that this Kw value comes as 10 to the power minus 14. Now, if this Kw value comes 10 to the power minus 14, we have already seen in previous case that H3O plus the square, you can write is Kw. So if we take log of it, minus log of Kw, so that will also be in case of this minus log of H3O plus. So we all know that this minus log of H3O plus comes the pH. So here in case of water we are writing as pKw. So it will come what now, minus log of 10 to the power minus 14 by 2. Now you are all thinking that what, why it became uh, by 2 and all that, because it has power 2, so it will be by 2, we all know. So then it will come 7. Now there's a trick that you can always apply, that if they give a value of you, that is any value, that is 10 to the power minus 16 or 10 to the power minus 6, they can give you any value. So and they ask you what will be the pKw. Okay, so at any temperature, just what we have to do, you have to just half this power, and that will be our pkw. Okay, so that's the trick here. So from this previous equation we have known that standard point of neutrality is 7. So let's write the pH scale, that is 7 for neutrality. And if it's get value more than 7, so this is the part of base. And if it's get value less than 7, that is this. So this is the part of our acid. Okay, so let's write again the formula for acid, that is minus log of H3O plus or H plus, and POH will be minus log of OH minus. But then what do we do in case of POH? To get value of any base's pH, we just pH of base, that is we just subtract it from our 14. Okay, so here it will come like this. So it will be our pH of base. Now what happens if there is the mixtures of acid? So let's see that. First is our strong acid and strong acid. Okay, so both are strong acid. SA, we will write it in SA. So for that we have a formula, that is the formula of normality. We will just take it from the first chapter and write it here. Let's suppose it is A1, A2, it is A1 and it is A2. So what will be it? It will be Na1 V1 plus Na2 V2, and here it will write V1 plus V2. So what we have written here, that is the normality of the first acid into its volume plus normality of the second acid into its volume by total of the volume. So in case of strong base and strong base, that is the first case, it is the second case, strong base and strong base, it's also the value of the total OH minus comes like this. Okay, NB1 plus V1, NB2 plus V2, here V1 plus V2. But what happens if it's a third case comes, that is strong acid and strong base? So for this case we have to see there are there can be two cases. That is that NaVa, that means the normality and volume product comes more than this NbVb, that means the bases volume and normality. So then we can only conclude the H plus, that will be NaVa minus NbVb by Va plus Vb. But what happens when the bases normality and volume product gets more than this acids normality and volume product? So then we have to go for OH minus, that will be NbVb minus NaVa by our Va plus Vb. Okay, so it is our third case. Now for the fourth case. Fourth case is of weak acid and weak base. Okay, so let's write it: weak acid and weak base. So for this we only get its H plus value, that will be our Ka1C1 plus Ka2C2. Okay, so here we know that Ka is our equilibrium constant of acid A, and C1 is concentration of it, and so K2C2 is the concentration of second acid or base. Okay, now the next things, that is our buffer solution. So let's write it: buffer solution. So what is buffer solution? That is the this, you can guess it from the name, but it has a significance that this buffer solution hinders the change in pH of solution. That means it always tries to maintain neutrality. Okay, so the solution becomes equal to 7, or nearly or almost equal to 7, its pH. So this is called our buffer action. Now there are two kinds of buffers. That is, first one is acid buffer. Okay, now what is acid buffer? Acid buffer is that contain weak acid and the salt of acid with strong base. That means weak acid plus salt of weak acid with strong base. Just remember it like this, it will be easier for you. Example given, what we can give the example, that will be CH3COOH plus CH3COOH Na. Now in case of second case, that is our basic buffer, right? So here in case of basic buffer, what we will see, that it is the solution of weak base and salt of that weak base with strong acid. Now what will be its example? It will be, let's NH4OH plus HCl, it will form NH4Cl plus H2O, right? So what will be the basic buffer here? That is NH4OH plus NH4Cl. Now we are going to see the formulas which makes this buffer solution. There are two formulas, that is pH of buffer solution when it is acidic buffer. So you can see that it will be pKa plus log of salt, that is concentration of salt, by concentration of acid. And when it will be acidic, not but basic buffer, it will be pKb plus log of concentration of salt by that concentration of base. Okay, so here is our buffer solution is done. Now what comes next, that is our sparingly soluble salt. Okay, sparingly soluble salt. Now in sparingly soluble salt, what happens that uh, that salt that doesn't dissolve completely but ionizes completely in aqueous solution is known as sparingly soluble salt. That means not dissolve completely but ionize completely. Okay, so let us see an example of this sparingly soluble salt, that is our AgCl. Okay, now if you add this AgCl into H2O, what it gives? It gives Ag plus plus Cl minus. Okay, so what happens that if we write its equilibrium equation comes like this. Now we have taken a certain amount of concentration of this AgCl, so it will be our constant. Now we can write this K into any concentration of the total salt, that is KSP, and that will be the value of this concentration of these two ions. Now there is a formula that is valid for sparingly soluble salt, that is KSP of any salt. Okay, it will be x to the power x, y to the power y, and s to the power x plus y. Now you are all thinking that what is this x, what is this y, and what is this s? We all don't know. So let's see what is x, what is what. So in previous equation we have written it right. So let us see with it with this equation that here x is our Ag plus, y is our Cl minus. So here you can see the coefficient of x, what that is. It is nothing here, not a for y it is also nothing here. So what is this x then? This is the coefficient of this Ag plus, and y is also coefficient of Cl minus. And what is the s here? S is the thing that is called solubility constant. Okay, so you can always come across this s thing in the sums that will be given according to this sparingly soluble salt. Okay, so if they give you another example, I am going to give you, that is for, let's see, CaCl. Now if write it like this, Ca2 plus 2Cl minus, right? So here you can see here x is also 1, but here y is 2. So what will be its KSP? It will be 1 to the power 1, 2 to the power 2, s to the power 1 plus 2. So that means 4s cube. Now if they give you the value of KSP or the value of s, so you can just conclude the value. If the value of s is given to you, so you can conclude the value of KSP. If the value of KSP is given to you, you can conclude the value of s, that is solubility here. So it is the shortest formula to do this. So there is the last thing that is remaining here, that is our hydrolysis. So let's go for that. Hydrolysis. Now to do hydrolysis, there has to be a criteria, that is NAV A has to be NBVB. That means what we have done for now, that is strong acid and strong bases case, that if any of them has the greater concentration and product of that normality value, then we can just minus it and then just uh, conclude its pH or POH. But here, if the concentration and normality product of acid and base becomes equal, then we have to do its hydrolysis. So in first case, if they are both strong base and strong acid, so then the pH comes 7. But what happens when this is the salt of strong acid and weak base? Okay, so then we have to write a formula for pH, that is minus 7 minus half pKb minus log C. Okay, now for the third case, that is strong base and weak acid, its pH will be 7 plus half into pKa plus half into log C. Now we have seen that this K is the equilibrium constant of that acid and Kb is the equilibrium constant for base. So for the fourth case, what is that weak acid and weak base, pH will be 7 plus half into pKa minus half into pKb. So here is our hydrolysis is also done, and with that hydrolysis our equilibrium is ended here.